Hello, this is part 1 of a lesson where we're going to learn about the moment of a force, or torque. Let me go over the topics we'll be covering. In part 1, which is this part, we'll cover some terminology you need to know, a bit of background, what is the moment of a force or torque, how do we calculate it, and some practice calculations. In part 2, separate video, we'll talk about how to use the centre of gravity of an object in moment calculations, talk about the principle of moments, and then do some more problem solving. Part 3, separate video, a few words about the units we're using. Then we'll talk about this more advanced equation for finding the moment of a force, do some problem solving, to finish off a few words about something called a couple, and then we'll talk about moments in terms of vectors. So, as we go through, there'll be 1 or 2 exercises for you to try. You may want a pen and paper. You don't need the calculator, as all the arithmetic is very simple. If you want to pause and get a pen and paper, now is as good a time as any. Before we dive in, let me just say briefly what the moment of a force or torque is, in case you're not familiar with the term. It's the ability of a force to make something rotate. Now, don't confuse the word moment with a short time, as in I'll be with you in a moment. That's not the meaning. Don't confuse the word moment with momentum, which is a different thing. The moment of a force is its ability to make something rotate. And we use different expressions when referring to it. We could say the moment of a force about a point, or the moment of a force, or just the moment, or sometimes we use the term torque, and torque is another word meaning moment of a force. I'm going to stick to using the word moment most of the time. When we do calculations, we can work out the moment. It's got a size. And the symbol we use, well, people use capital M's or sometimes a Greek letter tau, a small tau, which is that symbol. I don't like M because it looks too much like mass, so I will use tau to remind us of torque, tau. Let's talk about some terms you need to know. What are they? Fulcrum, point of application, and very important, line of action. Fulcrum first. What is a fulcrum? Well, it's basically just a posh word for a pivot. Suppose you have a seesaw, simple one, plank balanced on an edge like that, pointed edge. The point of contact is the fulcrum. It acts as a pivot. The top part, the yellow plank, can rotate around that pivot. And a fulcrum just means a pivot. It doesn't have to be something resting on an edge. It could be this sort of arrangement where you have a hinge. And a door hinge is a fulcrum. The joint in a pair of scissors is a fulcrum. So it's just a pivot in simple terms. What about these terms? Point of application of a force and the line of action of a force. Well, there's a block resting on the ground. Let's apply a force to it. 20 newtons to the left. The point of application is pretty obvious. It's a point on the object where the force is applied. So it's shown here by the tip of that arrow. What about the line of action of the force? Well, the line of action is a line which passes through the point of application and goes in the same direction as the force. So in fact the force lies on this line. Let me draw it. It's that blue line. That's the line of action of the force. In principle, it can be extended indefinitely to the left or the right, or whatever direction is relevant. And that's a very useful concept, the line of action of the force, a line that the force is on. Let's just look at another force, 20 newtons to the left. In vector terms, it's the same. It's got the same magnitude, it's got the same direction, but it's got a different line of action. The point of application is now up here, and the line of action of this force would be that. Which of those two forces do you think is most likely to cause this object to topple over, assuming there's friction at the bottom so it can't slide? Is one more likely than the other? I'm sure you know from your experience that the 20 Newton force at the top is more likely to make this topple over, and the turning effect of this force, 20 newtons, depends on how far the line of action is from the floor. Of course, a line of action doesn't have to be a horizontal or vertical line. If you have a force like that, where do you think its line of action is? You realise that would be the line of action. Right, now we can get on and talk about what we mean by the moment of a force, or torque. And I'm going to work out a couple of examples before I give you a definition. So let's take this very simple situation of a seesaw. What's going to happen if we put a weight on the right hand side? Well, you don't have to know excuse me, you don't have to know very much physics to know that the bottom of the right hand side will go down. So the whole seesaw has rotated clockwise because of this force on the right hand side. So we could say that the weight has a clockwise turning effect, or to use the language we want to, we can say the weight has a clockwise moment about the pivot. It's got a tendency to make this thing rotate clockwise about the pivot. What would I have to do to return the seesaw to the level? Well, one thing I could do is apply a force on the left. The weight was 10 newtons on the right. If I apply a force of 10 newtons on the left, the same distance from the pivot that the weight was, the 10 newton force will have the effect of making the seesaw rotate anti-clockwise or counterclockwise, purple arrow. So we can say that the force we've shown in purple has an anti-clockwise or counterclockwise turning effect, or in the language of moment we'd say it has an anti-clockwise moment about the pivot. It's got a tendency to cause rotation in an anti-clockwise direction, with the pivot being the centre of rotation. So get back to our horizontal balanced equilibrium state. Of course, I could achieve that by pressing it at a different point on the left of the seesaw. I could press a bit nearer to the fulcrum. If I did that, would I need a bigger or smaller force, do you think? And I hope you know from your experience that if you press nearer to the fulcrum, nearer to the pivot, you would need a bigger force than 10 newtons to balance it. So if applied nearer to the pivot, the balancing force needs to be bigger to provide the same turning effect, the same moment. Now, here's an example for you to think about. Let's look at an hexagonal nut. So I hope you know when you have a nut, usually you turn it clockwise to tighten it or anti-clockwise to loosen it. And we use a spanner, or some people call it a wrench, to do that. There's a rather crude spanner. Now, I'm going to ask you some questions. Let me mark a number of different forces you could apply to the spanner. Quite a lot. You can have a look at those in a minute, but what I want you to do is try answering these three questions. Which force or forces has or have a zero moment? That means no turning effect. So some of these forces may or may not make the nut turn. Can you identify which have a zero moment, no turning effect? Which force do you think has the biggest clockwise moment, the biggest clockwise turning effect? And which force do you think has the biggest anti-clockwise moment? Pause to think about those. Well, I hope you've done it. If you look carefully, forces A, forces D, and forces E point directly at the centre of the nut. And if you apply a D or E, they are not going to cause any rotation. They're directed at the centre, not to one side of the centre. So the answer to the first question was A, D and E. Which force has the biggest clockwise moment? Well, I hope you can see that only B and C have clockwise moments, and I hope you know that if you apply a force further away from the fulcrum, it has a bigger turning effect. It's a lever. So the answer to the second question is C. C is furthest away from the fulcrum and it will have a bigger turning effect than B. And the last one, similar argument, is G that's got the biggest anti-clockwise or counterclockwise moment. Now, let's look at another problem. There's a block standing on the ground. I've labelled the bottom right corner P. Bottom right corner. Let's put a force of 20 newtons to the right applied there, and let's say the point of application of the force is at a height of 2 meters above the ground. Let's add the line of action in, and of course if this force 20 newtons is horizontal, the line of action is horizontal, so the height of the line of action is also 2 meters, fairly obvious. How do I work out the moment, the turning effect of this force about point P? And it's a very simple calculation. The moment of the force about P is, what we do is take the force, 20 newtons, and multiply it by this 2 meters. And that's the distance from point P that we're interested in to the line of action. It's actually the shortest distance. So we don't take the distance from point P to the point of application. We say from point P we're going to take the shortest route to get to the line of action, and that's actually a line which is perpendicular to the line of action. So it's just a 2 meters. And the moment of the force about P is 20 newtons times 2 meters, or 40 newton meters clockwise. Look at the unit, we multiplied newtons by meters, so we call the unit the Newton meter. Don't put the meter in front of the Newton or it looks like millinewtons. NM, capital N, small m. And it's clockwise, we should say the direction. If you look carefully, the tendency of this force is to try and make this object move clockwise about P. Here's another example, the same object, P bottom right, force at a different angle now, different position. How do we work out the moment of this force about point P? Draw a line of action, and we want the distance from point P to the line of action. We want the shortest distance that we get by having a line perpendicular to the line of action through P. Let me draw it, you'll see what I mean. The moment of the force about P is, well, that's the line we want. That's the shortest distance from point P to the line of action. And it's the line perpendicular to the line of action. And let's suppose it's 2.5 meters, that white line. Well, the moment is simply 20 newtons times 2.5 meters, or 50 newton meters, anti-clockwise, if you look carefully. Let me give you a definition. Now on the bottom I've marked a force and a point. They could be anywhere. We'll refer to those in a moment. So the moment of a force about a point is, this is the definition, the product of, we're going to multiply together two things. So it's the product of the magnitude of the force and, this is a difficult one, the perpendicular distance, d, between the point and the line of action of the force. Say that again. It's a perpendicular distance between the point and the line of action of the force. So look at the diagram at the bottom. There's the force, and we want the moment of this force about this point P. Draw the line of action in. Draw a line from P that's perpendicular to the line of action. It's that line there. That's what we mean by the perpendicular distance. It's that distance along that line from point P to the line of action. And that line in white is perpendicular to the line of action. And show that, in fact, it's perpendicular with a little angle bracket there. The moment is simply the force times the distance. Or in terms of the symbol tau for moment, F times d. Okay, time for you to do something. Here's a two-stage problem. I want you to try sketching the diagram first, and once we've checked that, we'll do the actual calculation. 3 meter long horizontal plank is pivoted at its center. A vertical downwards force of 50 newtons is applied to the left end. We want to find the moment of the force about the pivot. So your first task is to draw a diagram to represent this situation. Pause and try that for yourself. Well, I hope you've drawn a suitable diagram. Maybe something like this. Doesn't matter what type of pivot you have, it could be anything, but you should have a plank. Should have a pivot in the middle. We should have a 50 Newton force to the left end, and we should really include the distances. So it's a 3 meter long plank and the pivot's at the middle, so it's 1.5 meters on either side. And then the last part is easy. You can pause if you want to do it for yourself. What's the moment of the force about the pivot? Try that for yourself now. Hope you did it. Draw in the line of action if it helps you. The moment is force times distance. It's 50 newtons times, well, the distance from the pivot to the line of action is this 1.5 meters, isn't it? So it's 50 times 1.5, or 75 newton meters. And I hope you can see the tendency of this force is to try causing anti-clockwise rotation about the pivot. So 75 newton meters anti-clockwise. Another problem for you. Here's a block side view. I've called the bottom left corner P. Now I've given you some dimensions here. I'm going to mark some forces on here. So we're going to apply forces A, B and C as shown, and your task is simply to find the moment of each force about point P. So pause and try that for yourself. Let's go through it. Do A first. What's the moment of A about P? Well, we don't have to draw the line of action, and you can imagine it. The line of action goes straight down. It actually goes through point P. So it's 0 distance away from point P. So the moment of A about P is 8 newtons times nothing, which is 0. And if a force passes through a point, or its line of action passes through a point, it's got no moment about that point. What about B? The moment of B about P, well, it's 10 newtons. Imagine the line of action drawn in. Hope you can see the line of action would be a distance of 1.5 plus 2.5, 4 meters. So the moment of B about the point P is 10 newtons times 4 meters, 40 newton meters, and I hope you can see its effect would be anti-clockwise. What about the bottom one? Moment of C about P, same thing. I hope you can see it's simply 4 newtons times 1.5 meters, that's the distance. So 6 newton meters clockwise. And a slightly tricky one to finish with. Let's have a block here. I'll call the bottom right hand corner P. I'll have a 1 kilonewton force now at this angle. Let me give you some values. Let me put the line of action of that force in. I'll tell you the height of the block is 10 meters. I'll tell you this distance is 17.32 meters. I'll tell you this angle is 60 degrees. And if you need it, the object of course is to find the moment of the force about P. Find the moment of this 1 kilonewton force about P. And if you want to use them, I've given you the values of sine, cos and tan of 60 degrees. So pause that, read it through for yourself, have a good think. I hope you've tried it. We know how to work out moment. It's a force times distance. The hard thing is usually working out which distance to use. Now I've put some red herrings in there. We don't need all the information I've given you. What distance should we use? We want the moment about P, so we've got to go from P to the line of action and take the shortest route. Draw a line that's perpendicular to the line of action and goes through P, and it's this line. and we want this length d. Now, how do you work out d? Look at this triangle here. Got a 60 degree, 30 degree, 90 degree triangle. What do we know about the sine of an angle? I hope you know sine is the opposite side over the hypotenuse. And we can use that here. D divided by the hypotenuse, which is 10 meters, is sine of 60 degrees. Can you see that? D over hypotenuse. Let's write that. D over 10 is sine 60, which is given to you, 0.866. So D is 0.866 times 10, which is 8.66 meters. So we've worked out the distance we need. Moment is then very simple. A kilonewton's 1,000 newtons, so that's 1,000 times 8.66, or 8,660 newton meters. And I hope you can see the force is tending to cause anti-clockwise rotation about P. So anti-clockwise. That's it. I hope that makes sense. In part 2 we'll continue and learn how to deal with more complex situations. Thank you for watching.